Hello everyone, welcome back to another video tutorial for strength of materials topic. But in this video, we will talk about deflection of beam. Okay, but to be specific, in this video, we will learn to compute deflection of beam due to bending. Okay, now like for example, if we have a beam and this beam is being subject to a transverse load, let's say that's concentrated load P, then due to that load, there would be a deflection or a change in the position of our point in our beam. Like for example, this one, we have this deflection in which there is a movement of, let's say it's our point Y to at this point, let's say it's Y prime. Okay, so there is a deflection caused by loadings. So in this video, we will learn to compute this deflection at any point in our beam. Okay, so we have different approach that we usually adopt in computing for the deflection. Okay, but the most common two of this method are the double integration method and the moment area method. We have still another method. We have virtual work, Castellano theorem, and so on. But in this video, we will only learn double integration method and moment area method. A double integration method is used to determine the equation of our deflection diagram. Like again, for example, this one, we have uniformly distributed load. Okay, and we have a simply supported beam. Now we know that this is continuous since we do not have other loads acting from A to B. We only have uniform load. So therefore, we could have only one moment equation in this beam. Okay. Now, if we have this transverse load acting, therefore we also have a deflection in our beam, and that would give us this deflection diagram. So I'm trying to draw it exaggeratedly now, and this deflection diagram here is just a graph or a, let's say this is Y. It is just only a function of our X, in which our X here, that is just the distance from any specific point in our beam. Like, but the most commonly reference for our X is the end support. Okay, so therefore we can say that this deflection diagram here can be drawn, okay, or can be plot in our Cartesian plane using these equations in which Y, or this is the deflection, as a function of X. So this would be our goal in double integration method. We should come up with an equations, and this equation that I was referring to was this one, and we have the relationship of our moment equation. This is the internal moment equation that we could come up by cutting our beam at any specific point, is equal to, we have the second derivative of Y, this is the deflection, over the derivative of X squared, in which this X here, that is the distance from the end support to any specific point in our beam. Okay, now by double integrating this one, we could come up EI Y, where EI here, this is the flexural rigidity, E is the modulus of elasticity, and I is the moment of inertia. But if we have an asymmetrical beam, then we need to compute using transfer moment of inertia. Okay, then this is our Y here. Again, this is the deflection. Okay, then we have the double integration of our moment equation. Then since we are integrating this one, then we could come up with two constant. By this C1 here, this is included by first integrating our derivative. Then this C2 here occurs when we integrate again our equation. So therefore, the C1x here occurs during our first integration process, and C2 here happens or occurs during our second integration process. So So we can come up with our equation of deflection, which is this one, EIY is equal to the result of the double integration of our moment equation. Now, for sign convention, now when we have a vertical deflection which is upward, then that's positive. If it is our deflection is like this one, okay? Let's say this is our beam. So if we have this deflection here, this is a positive deflection, and if we have this type of deflection, then this one is negative deflection. Since we have deflection, there would also be a rotation of our beam. And rotation happens when we have a hinged and ruler support. Again, when we have a fixed support, we do not have rotation to this one. Okay, so our y prime, so this is 0. But in this case of hinge and ruler support, we have rotation in our beam. It's theta. Okay, and then if we have a counterclockwise rotation, that is positive. Now for clockwise rotation, that is negative. Double integration can be very useful when you have a continuous beam. Again, when we see continuous beam, when we have the same load all throughout from one segment. Okay, like the one that I presented, this one, this is an example of a continuous beam since we do not have other load within A to B. Okay, we only have a uniformly distributed load. But once we introduce a concentrated load here, P, so there would be a discontinuity between A to B since P here causes discontinuity in our beam. So therefore, our diagram here, or deflection diagram at this point here is different from the deflection diagram of this point. So therefore, we need to come up with two functions, okay, or two equations for deflection diagram in case of we have a discontinuity in our beam. Now in that case, it would be very tedious and time consuming, okay, in using double integration because a new set of function must be developed for each interval of the beam. So you need to develop an equation from A to this point and from the concentrated load to B. So therefore, it would be very difficult to compute for our Y. So in that case, we have a new method or a direct method which is known as a Macaulay function. Now in Macaulay function, now if we have a bracket function like this one, x minus a raised to the n, when our x here is lesser than a, therefore our value inside the bracket is negative, then we need to cancel that out, and when we have x lesser than a, that is always equal to 0. Now if we have our x here is equal or greater than a, then that's the time that we remained our function. Then we can use x minus a raised to the n. Again, if we have negative answer inside the bracket, then we equate that as 0. Otherwise, we continue our evaluation of our function. And that's how Macaulay is being used. Now, this is very helpful, especially when dealing with a discontinuous beam. So you do not need to come up with equations, okay? Multiple equations. You just only need one equation and one cutting section to compute for the deflection. But still, you can try to solve it using the conventional or traditional approach for double integration. No? Like for example, if you have this beam here in which there is a discontinuity in our beam, okay, as what you can see, we have a uniformly distributed load as well as we have a concentrated load. So in that case, we could come up with 3 segments in this beam since our beam is continuous from A to B. We also have continuous beam from B to C and C to D. So using double integration here would give us 3 equations, okay? And that equation is from this one by cutting at AB and by cutting at BC, within BC, and by cutting at or in between C and D. So we need 3 equations here. We might encounter difficulties here in computing for our constant C1, C2, okay? The one that we develop by integration, or that's the arbitrary constant. So in this type of beam, instead of cutting it every segment, we can come up, or we can cut it by just converting this beam into a continuous beam. So we just need to extend our load. So this width here must be extended up to D. However, since there is a new load introduced, then we have to introduce a counteracting load with equal magnitude, okay, like this one, so that it would remain the same. Okay, so there would be, since if we have W here, unit load with here, and then we introduce another W load here below, then there would be balance in our beam, as if that we did not introduce another load in our beam. Okay, that's the purpose why we need to have the same load acting opposite. Okay, in that case, then we can just cut our beam at this point. So by cutting only at one section gives us the answer for the deflection at any point in that beam without having any trouble in evaluating the functions. Okay, so that's how Macaulay function or Macaulay method is very helpful, no, in dealing, especially if we have a discontinuous beam. Okay, so let's try to solve a problem or apply the concept of double integration. And then we have an example here. Determine the maximum deflection and its location, and also determine the rotation at support B. When we have our beam cross-section as 80 by 40 millimeter and the modulus of elasticity is 12 gigapascal. So we have this, our simply supported beam with a concentrated load 600 Newton, which is 2 meters from A. Okay, now as what I have said, this concentrated load here, 600 Newton, causes discontinuity in our beam A to B. So therefore, we need to come up with two cut section to this one, and our cut section should be from A, let's say this is C, from A to C, this is one continuous segment, and from C to B, this is another continuous segment. Okay, now using double integration with this type of beam which is discontinuous will give us difficulties in computing for the deflection, since again we need to come up with two functions here, and then that function is from A to C and C to B, since again these two segments here have two different deflection function or deflection equation. So in that case, we need to apply Macaulay method. However, you can still use or do the usual double integration method in this beam. However, it might be very tedious, okay? Since again, we need to come up with another equation or functions. Now, in Macaulay method, we just need to cut this beam into one section, and that section will be taken from the farthest segment from our reference point, and our reference point here is A. So therefore, our cut section here could be taken at this point here. Let's say this is our cut section 1. Okay, so this is X distance from our A. Now, but before we can compute for our equation or moment equation here and shear equation, we need to compute first our reaction. Since this is a hinge, so we have two reactions at that point, but then since we do not have horizontal forces in the beam, so therefore we only have one reaction in this point A. We have, let's say it's RA, and this one is ruler, then we have here RB. Okay, so we can compute RA and RB here by first summing up moment with respect to B, and this equals to 0. Then counterclockwise positive, we have 600 Newton times the moment arm from B, we have 4. Then minus RA, the moment arm from B is 6 times RA. and equals to 0. So we have RA here, which is equal to 400 Newton. For RB, we just need to sum up forces. Vertical is equal to 0, upward forces are positive. Then we have RA plus RB minus 600 is equal to 0. Then we have RA here, 400 plus RB minus 600 is equal to 0. Then we have the value of RB here, which is equal to 200 Newton. Okay, so we have computed now our reaction, which is for A and B, which are 400 and 200 newtons respectively. Then after that, we can now proceed by cutting our beam. Now take note, once we cut our beam at this point, we could have our internal shear and internal moment exposed. So we have our internal shear here, let's say that's positive since this is downward on the right face. Then we have our positive moment since it causes smiling bending. Okay, that's moment. Let's set moment 1. So we can isolate this section. Then we have here. Then we have this section here. So we can now create a moment equation, which is which sum up moment from section 1 is equal to 0, counterclockwise positive. We have 600 Newton times the moment arm from section 1. We have this x minus 2. This is the distance. So we have x minus 2. Then we have the moment due to the reaction A, which is 400 times x. Okay, then we have the moment, the internal moment at section 1, which is plus m. It gives us 0. So we have our moment equation here, which is equal to 400x minus 600x minus 2. Now, in Macaulay method, it is very important that you do not distribute the value 600 inside the bracket, since this is the one, or this is the Macaulay bracket. Stay this expression here as it is. Okay, you do not need to distribute 600 inside our bracket. So this would be our moment equation. In double integration, just like what I said, we have the flexural rigidity, this EI here. Then we have the double differentiation of y. We have the double differentiation of y with respect to x. Okay, and this equals to the moment. And this moment here should be a function of x, since we can evaluate this as EI. The second derivative of y is equal to m. Then this is the derivative of x squared. And then let's have the first integration of this function. They would come up with EI. Now take note, this d squared y here is the same as with y double prime, correct? Is equal to, now our moment equation here is 400x minus 600x times 2. Then we substitute the value of our moment to this, the integration. So this is the function of x. So this one is moment as a function of x dx. So we have the integration of 400x minus 600x minus 2, and then we have dx. Okay, then we integrate that. In first integration, we have the integration of double derivative of y gives us first derivative of y is equal to this one here. We have 400 x squared over 2 minus 600 x minus 2 squared over 2 plus c1. So we have, by further evaluation, we have here EIY prime is equal to 200 x squared minus 300 x minus 2 squared plus c1. So this is now the equation of our slope. Since we have first derivative, and from our differential calculus, we know that first derivative is just the slope of our curve at any point. Okay? Now, let's continue our integration of this function to come up with the equation of our deflection. Okay? So, we integrate this again. with respect to dx, then we have here the flexural rigidity EI, then the integration of the first derivative gives us y, in which y here, this is the deflection, is equal to power rule. We have 200 x cubed over 3 minus 300 x minus 2 cubed over 3, correct? Then, since we have constant here, the integration of constant with respect to dx, then we have c1x. But since we integrate it, we need to have another constant, that is c2. Okay? So this is now, or by further evaluating this one, we have EIY is equal to 200 over 3 x cubed minus 100 x minus 2 cubed plus c1x plus c2. So this is the equation of our deflection. So we will be using these equations, this equation of slope and equation of the deflection, to compute for the rotation at point B and the maximum deflection respectively. Now, as what you can see in our equation, we have arbitrary constant C1 and C2. So we need to compute for our value of this arbitrary constant by setting a boundary condition. Okay? So we have our first condition here that we know if our x here is equal to 0. So our first boundary condition here is that when we have x here is equal to 0, so the point is at the support A. When our x equal to 0, we do not have a deflection, correct, at this point, unless we have settlement at A. But in this case, that our A here is rigid, okay, or our A here has no settlement, so therefore it remained at this point even though that there is a load acting at this beam. Okay, so therefore our A here has no vertical deflection, so we can say that our y at that point is 0. So when our x equal to 0, then our y is equal to 0. Then we could also have at this point here, we have at x is equal to 6, we also don't have a deflection at that point since this is a ruler. Okay, we don't have a settlement at this point, so therefore the position of our ruler support remains at this exact point here, so there will be no movement in vertical axis. Okay, so this would be our initial condition that we will be using in computing for our arbitrary constant 1 and 2. Okay, this is the equation of our deflection diagram. Now, we know that our first condition is when our x is equal to 0, our y is equal to 0, or our deflection at the support A is 0. So we substitute everything to this equation. Then we have EI times 0 is equal to 200 over 3 times 0 minus 100 times 0 minus 2 cube plus C1 times 0 plus C2. Now take note, in Macaulay method, if we have our x minus a here raised to n, and this value is lesser than 0, or that is in negative, so therefore we can say that this is equal to 0. That is the advantage of a Macaulay method. Now, otherwise, if you do not use Macaulay method, then you need to cut it twice. So we need to cut it at point A to point C and point C to point B. So these boundary conditions here is invalid when we have our cross section at this point, since again we have different equation from A to C. So this condition x equal to 0, y is equal to 0 is invalid for this section, or for the equation from C to B, since again our condition is at the support A, in which we should have the equation from A to C. Okay? Now, since we are using Macaulay method, so this becomes valid, or this boundary condition becomes valid for our cut section at this point. So therefore, since this is 0, okay, this one is 0, now we have inside the bracket here 0 minus 2, this is negative 2. Again, this is a negative value, this is less than 0. So therefore, we can automatically say that this is equals to 0. Okay? And this one is 0, so therefore, our value of C2 here is equal to 0. Okay? Now, since we have already the C2, we have already determined the C2, now we go to the determination of C1. We have another boundary condition, which is when x is equal to 6 or at support B or at B, we have our deflection at support B is equal to 0. So we substitute these values in our deflection equation, then we have EI or deflection rigidity times 0 is equal to, we have 200 over 3 times, we have the value of x here, this is 6 cube, correct, minus 100 times x minus 2, this one, we have 6 minus 2 raised to the 3 plus C1, now this is the one we're computing here, times 6. Now, our value of C2 from our previous answer, we have C2 which is equal to 0, then we can go directly here as C2 as 0. So we have our value of C1 here. By further evaluating the equation, we have to negative 4,000 over 3. So we have now the values of our arbitrary constant C1 and C2. Okay? So we have our final equation, which is for the equation of the deflection. We have EIY is equal to 200 over 3 x cube minus 100 x minus 2 cube. Now our C1 here, that is negative 4,000 over 3 x, and our C2 is equal to 0. So therefore, this is the equation for deflection. Now for the slope, we have to use this equation here. Okay, we have EIY prime is equal to 200x squared minus 300x minus 2 raised to the 2 plus C1. We have EI or the flexural rigidity, then the first derivative of y is equal to 200x squared minus 300x minus 2 squared. Then we have the C1, the value of C1, which is equal to negative 4,000 over 3. So this is the equation for the slope. So we can now compute for the maximum deflection and its location. Now, going back to the beam, so if we have 600 Newton, we do not know where is the location of our maximum deflection since this is not symmetrical. Okay, and our 600 Newton here is not acting on the midspan. So therefore, the maximum deflection could be anywhere within this beam here. So let's say that our deflection is this one. So our maximum deflection here could be at this point. Let's just assume that it is at this point. So it's our y maximum, okay, the maximum deflection. And then let's say this is at x max, okay, from A. So our goal here first is to compute for the x max, the location of the maximum deflection, which is this point. So if we found the location of our maximum deflection, then we can now use this value of x max in our deflection equation. Okay, so that we can compute for the value of y at this x max here. But how are we going to compute for this distance or the location of the maximum deflection? Now take note from your concept of differential calculus, at the maximum point of a curve, if this is a maximum point, our slope at that point, okay, is equal to 0. So therefore, the first derivative of the curve at this point is equal to 0. Okay? Since again, at the maximum or the minimum point, this one, So our slope is always equal to 0. So that's the concept from your maxima and minima in your differential calculus. So therefore, we have to use first the slope equation, okay? And we set our y prime at that equation equals to 0. Okay, so we use this equation for slope by setting our y prime here is equal to 0. This is the location of our maximum deflection, that's x max. So we can substitute here the value of 0. So we have EI, or the frictional rigidity times 0, is equal to 200. Let's say this one is x maximum squared minus 300 times x maximum minus 2 squared is minus 4,000 over 3. Okay, so we can you compute for the value of x here by further evaluating this equation, but by just using your calculator, we can come up with the value of x. So we input everything on our calculator, then we have 200, then x squared minus 300, then the parenthesis x minus 2 squared minus, we have 4,000 over 3, then equals 0. So we have the value of x here, just shift solve, then we have 2.734, that's the value of x. X maximum is equal to 2.734 meters from A. So we have the location of our maximum moment, which is at this point. Okay, that is 2.734. So we have incorrect assumption. So this one is our maximum, which is at 2.734 from A. So this is the location of our maximum deflection. So we can now compute for y max, the maximum deflection, by using the deflection equation, which is this one here. Okay, so we have our frictional rigidity times the maximum deflection is equal to 200 over t. Now the location of our maximum deflection is at 2.734, okay, cube minus 100 times 2.734 minus 2 cube minus 4,000 over 3 times 2.734. So we have our maximum deflection with respect to frictional rigidity, which is equal to negative 2322.479. Okay, and this unit here is in Newton meter cube. Okay, since this one here is in Newton, 200 Newton, then x here is in raised to the 3, so therefore we have meter cube. Okay, so we have our maximum deflection, which is equal to negative 2322.479 Newton meter cube over the flexural rigidity EI. Okay, since our beam section was given, we have our beam which is 80 by 40 millimeter. So we have 80 height and 40 millimeter width. So we can compute for our I, which is the moment of inertia of a rectangle, which is BH cube over 12. This gives us our B is 40, height is 80 cube over 12. Then we have our I here, which is equal to 170,666.667. The unit is in millimeter to the fourth. And our E here, it was also given. We have 12 gigapascal, okay, or 12 times 10 raised to the 3 Newton per square millimeter. So we can now substitute this value of EI in our equation. So we have negative 2322.479 Newton times cubic meter. Now take note, this is in meter cube, so we need to convert it into millimeter. So we multiply 1000 raised to the 3, correct? Over our E here is 1706, then 666.667, that is in millimeter to the 4th, times our I is 12 times 10 raised to the 3 Newton per square millimeter. Then since we multiply this into 1000 cube, then we have here the unit is in millimeter cube. So we can cancel out Newton, and then we have millimeter squared, and then the remaining would be millimeter squared here. Now take note, we have millimeter cube here. We can cancel this out, and millimeter squared. The remaining would be in millimeter. So we have our answer here, which is equal to negative 113.402 millimeter, which is, since this negative, so therefore this is downward deflection. Okay, as what you notice here, it is quite large. Okay, since again we have a very small cross section, we have 80 by 40 millimeter, and then we have 600 Newton load, so obviously it would have a very large deflection. Now, and this is the maximum deflection happened at 2.732 from meters from A. So this is our answer for question letter A. And now let's compute for the slope at support B. By using the slope equation here, we have determined already. So we compute our y prime when our x here. We know that at support B, our x is equal to 6, correct? So we substitute the value of x in our equation. Then we have EI y prime is equal to 200 times 6 squared minus 300 times 6 minus 2 squared minus 4,000 over 3. We have our y prime here in terms of flexural rigidity, which is equal to 1066.667 over EI. So we have the unit here, since this is in Newton and this one is in meter, so we squared it, so therefore we have meter squared. The unit of our slope is in Newton, meter squared. Okay, now our EI, we have already computed this one. Our E is 12 gigapascal, so we write it in our denominator. We have E here, it is 12, now times 10 raised to the 3 Newton per square millimeter, times our I here, 1706, 666.667. The unit is in a millimeter to the 4th, that's the I. Okay, then we can cancel here millimeter squared. The remaining at least is millimeter squared. Now take note, our numerator is in Newton meter squared, so we convert it into millimeter by multiplying 1000 squared. So we have, now we can cancel here millimeter squared and Newton. Then we have our answer here, which is in unitless, 0.0521, and this is in radian. Okay, since that is unitless. Now since this is positive, so therefore we have our slope here, which is counterclockwise. So we have counterclockwise slope at support B. So this is now our answer for the slope at support B. Okay, so I have another example in the second part of this video. So thank you for listening.